Look at the night sky right now. Close your eyes and imagine. You see that deep darkness, that black void stretching infinitely in all directions. It's beautiful. It's mysterious. It's even poetic. But wait a second. Have you ever stopped to think that this darkness shouldn't exist? That, in fact, this peaceful scene that calms us hides one of the most disturbing mysteries in physics. Let me explain what I mean. We all learned in school, that there are billions and billions of stars in the universe. I'm not talking about thousands. I'm not talking about millions. I'm talking about a number so absurdly large that our brains can't even fully process it. Just in our galaxy, the Milky Way, there are about 200 to 400 billion stars. And there's more. Our galaxy is just one among trillions of galaxies in the observable universe. Each of these galaxies has billions of stars shining, burning hydrogen, releasing light in all directions. So here's the question that will forever change how you look at the sky. If there are so many stars, literally countless stars in every direction, why the hell is the night sky dark? Think about it. If you look in any direction in space, eventually your line of sight should encounter a star. It's like being in a giant, dense forest. No matter where you look, you'll see a tree. The sky should be a blinding glow, every bit of it illuminated by some distant star. The night should be as bright as day. But it's not. The night is dark, frighteningly dark. And Richard Feynman, one of the most brilliant physicists of the 20th century, had something very specific, very brutal to say about this. He didn't accept easy answers. He wasn't satisfied with explanations that sound good but don't work. He wanted the naked truth, even if that truth was disturbing, even if it challenged everything we thought we knew about the universe. And the answer to this question, my friend, will reveal not only why the sky is dark, but will also expose deep truths about time, about space, about the origin of everything, and about the final destiny of the cosmos. Why doesn't anyone question this? Why do we spend our entire lives looking at the dark sky and find it normal? The darkness of night seems so obvious, so natural, that it doesn't even cross our minds that something strange is happening. But scientists, real scientists, they don't accept the obvious without questioning. They take what everyone assumes is true and ask, wait a minute, does this really make sense? And when you apply this mentality to the night sky, the whole thing falls apart. Let's think together. If the universe is infinite, and if stars are distributed uniformly throughout this infinite universe, then mathematically, necessarily, the entire sky should be glowing. Imagine you're at the center of a giant sphere. Each layer of this sphere, each spherical shell around you, contains stars. The first layer, the closest one, has few stars, but they're bright because they're nearby. The second layer has more stars, but they appear dimmer because they're farther away. The third layer has even more stars, even dimmer. But here's the crucial mathematical trick. As you go to more distant layers, the number of stars increases proportionally to the surface area of the sphere, that is, proportionally to the square of the distance. But the brightness of each individual star decreases also proportionally to the square of the distance. These two effects cancel each other perfectly. This means that each layer, no matter how distant, contributes the same total amount of light. And if the universe is infinite, you have infinite layers, infinite equal contributions of light. The result? Infinite light, an infinitely bright sky. But this clearly isn't what we observe. So something is deeply wrong with this logic. Either the universe isn't infinite, or the stars aren't uniformly distributed, or there's something else, something fundamental about the nature of the universe that we're leaving out. Feynman loved this kind of contradiction. For him, when mathematics says one thing and reality says another, that's where real knowledge lives. This question isn't new. It has a name. It's called Olbers's paradox, named after a German astronomer called Heinrich Wilhelm Olbers, who clearly formulated the problem in 1826. But actually, the question was known before him. Johannes Kepler, back in 1610, had already thought about this. Kepler was one of the giants of astronomy, the man who discovered the laws of planetary motion. And he realized that if the universe were infinite and full of stars, the sky couldn't be dark. Kepler's solution was simple and almost naive by today's standards. He said, well then, the universe isn't infinite. There must be an edge, a boundary beyond which there are no more stars. Problem solved, right? Not exactly, because this solution created other problems. If the universe has an edge, what's beyond the edge? And why would the universe stop right there? What kind of structure or cosmic wall could hold the universe? And there's more. Even if the universe had a finite size, if it existed for infinite time, the light from all the stars, no matter how distant, would eventually reach us. Given enough time, and the light from every star in the universe would fill every point in space. So now it's not just a question of infinite space, it's also a question of infinite time. And then things get even more complicated. In the 19th century, other scientists tried to solve the paradox in different ways. Some suggested that maybe there's dust in space, clouds of particles that block the light from distant stars. Seems reasonable, doesn't it? But Feynman, being Feynman, immediately saw the problem with this idea. If there's dust absorbing light for billions of years, that dust will heat up, and hot matter emits radiation. Eventually, this dust would get so hot that it would start glowing as much as the stars it's blocking. You haven't solved anything, you've just changed the source of light. So this explanation doesn't work either. Another scientist suggested that maybe the light from the most distant stars is somehow deflected or lost. But again, conservation of energy. Energy doesn't disappear. If light is being deflected, it has to go somewhere, and eventually it would end up contributing to the brightness of the sky anyway. It was as if every attempt to solve the paradox created another equally difficult problem. Before we continue, I want to pause here and ask something. Leave a comment right now telling me, what do you think is the real answer? Do you think the universe has an edge? That it's not infinitely old? Or do you have some other theory? I want to know how you're thinking about this before we reveal the real solution. And here's the most interesting part. Most people who comment always have a different theory. And this shows exactly how deep and non-intuitive this problem is. Many people think it has to do with the speed of light, or with the expansion of the universe, but the exact reasons are more subtle and more fascinating than any theory you might imagine now. So go ahead, leave your comment. Don't be embarrassed to be wrong. The greatest scientists in history were wrong about this for centuries. You're in good company. And besides, this exercise of trying to solve the problem on your own, of proposing a solution before knowing the answer, is exactly what Feynman defended as the best way to learn physics. It's not about memorizing facts. It's about thinking, questioning, proposing hypotheses, and testing those hypotheses against reality. So pause the video for a second, think carefully about this, and leave your comment. I'll really read it. I'm curious to see how many people will get close to the real answer. Now let's start unraveling this mystery for real, layer by layer, exactly as Feynman would. First, we need to understand what really happens when we look at the sky. When you see a star, you're not seeing the star as it is now. You're seeing the star as it was when the light left there. That's because light has a finite speed. It travels at about 300,000 kilometers per second, which seems extremely fast, and it is. But the universe is so absurdly large that even this incredible speed results in significant delays. Light from the sun, for example, takes about 8 minutes to reach us. This means that when you look at the sun, you never actually see the sun as it is at that exact moment. You see the sun as it was 8 minutes ago. If the sun exploded right now, you wouldn't know for 8 minutes. You'd continue seeing the sun shining normally until the light from the event arrived. Now let's go further. The star closest to the sun, Proxima Centauri, is about 4.2 light-years away. When you look at Proxima Centauri, you're seeing light that left there 4.5 years ago. You're literally looking at the past. Go even further. Some of the stars you see in the night sky are hundreds or thousands of light-years away. And galaxies? The Andromeda Galaxy, the nearest large galaxy to ours, is about 2.5 million light-years away. The light you see from Andromeda left there when our hominid ancestors were just beginning to walk upright in Africa. And now comes the crucial part. If the universe has a finite age, let's say about 13.8 billion years, as we know today, then the light from stars and galaxies that are more than 13.8 billion light-years away simply hasn't reached us yet. It doesn't matter how many stars exist out there. It doesn't matter how bright they are. If their light hasn't had time to cross space to us, we can't see them. It's as if there's a cosmic horizon, a boundary beyond which nothing can be seen, not because nothing exists there, but because light hasn't had time to make the journey. This is the first big insight. The universe isn't infinitely old. It had a beginning. And this beginning fundamentally limits how much light could have reached us, no matter how many stars exist. But wait, this alone doesn't completely solve the paradox, because even if we only consider stars within this cosmic horizon, there should still be billions and billions of them, and the sky should still be much brighter than we observe. So there must be something else happening. And here enters the second fundamental element, the piece that really completes the puzzle. The universe isn't static. It's expanding. And it's not just expanding in the sense that galaxies are moving away from each other. Space itself between galaxies is stretching, dilating, growing. Think of this like a balloon being inflated. If you draw dots on the surface of the balloon and start blowing, the dots move away from each other not because they're moving across the surface, but because the surface itself is expanding. This is what's happening with the universe in 3 dimensions. And this expansion has an incredible and crucial consequence for our paradox. Light traveling through expanding space is stretched along with the space. Imagine a light wave like a spring. If you stretch space, you stretch the spring. And when you stretch a wave, you increase its wavelength. Light with longer wavelength is redder light, of lower energy. This phenomenon is called cosmological redshift. The more distant the galaxy, the longer the light has traveled through expanding space, and the more stretched, more redshifted it becomes. And here's the crucial point. Light from the most distant galaxies isn't just shifted to visible red. It's shifted beyond red, to infrared, to microwaves, to wavelengths our eyes can't even detect. These galaxies are still there, still emitting light, but the light arrived to us so stretched, so transformed by the universe's expansion, that it doesn't contribute to the visible brightness of the night sky. It's as if the most distant stars are being gradually erased, not because they stopped shining, but because their light was transformed into something invisible by the very dynamic structure of the cosmos. And there's more. The expansion is accelerating. The most distant galaxies are moving away from us faster than nearby ones. And those beyond a certain distance are moving away so fast that their light will never reach us, no matter how long we wait. They're beyond our cosmological horizon forever. Feynman loved this kind of result. A brutal truth, as the title says. The universe is dark, not because there aren't enough stars, but because the universe is finite in age and is expanding. We're limited by time and by the dynamics of space itself. We can't see everything. We never will. There's a fundamental limit, imposed by the nature of the universe, on how much of the cosmos we can observe. Let's connect this to something even deeper. Richard Feynman wasn't the first person to think about Olbers's paradox, but he had a unique way of framing the problem. For Feynman, physics wasn't about memorizing facts or equations. It was about developing intuition, about asking questions like, "What's really happening here?" and not accepting superficial answers. He would say something like, "Forget what you learned. Start from scratch. Look at the sky. It's dark. Why?" And then he would build the explanation step by step, layer by layer, always asking himself, does this really make sense? Does this fit with everything else we know? One of the things Feynman constantly emphasized was the importance of not settling for verbal answers that sound good, but have no real content. He gave the example of students who can repeat definitions perfectly, but don't understand what they're saying. You can say, "The universe is expanding," but if you can't explain what that really means, what the observable consequences are, how we know it's true, then you don't know anything. You're just repeating words. So let's do this right. Let's get into the details. How do we know the universe is expanding? In 1929, an astronomer named Edwin Hubble, using the 100-inch telescope at Mount Wilson in California, made a discovery that changed everything. He measured the redshift of distant galaxies and noticed a pattern. The more distant the galaxy, the greater the redshift. And the redshift was proportional to distance. This means that more distant galaxies are receding faster. The relationship is linear. Recession velocity equals Hubble constant times distance. This constant, called the Hubble constant, has a value of about 70 kilometers per second per megaparsec. This means that for each megaparsec of distance, approximately 3.26 million light-years, the galaxy is receding about 70 kilometers per second faster. So a galaxy at 10 megaparsecs is receding at 700 kilometers per second. One at 100 megaparsecs, 7,000 kilometers per second. And so on. The farther you look, the faster galaxies are receding. And the only explanation consistent with this is that space itself is expanding uniformly in all directions. But here's where Feynman would really shine. He wouldn't just accept the universe is expanding as a final explanation. He would ask, expanding from where? If everything is moving away from everything, is there a center? And the answer is no. There's no center of expansion. Every point in the universe sees all other points moving away from it. It's the very structure of space that's growing, not objects moving through fixed space. To understand this, think again about the balloon. If you're an ant on the surface of the balloon, and the balloon is being inflated, all the other ants appear to be moving away from you. And each ant thinks it's the center. But none of them is actually at the center, because the center is inside the balloon, in another dimension that the two-dimensional ants can't perceive. Similarly, we live on the surface of a three-dimensional space that's expanding in dimensions we can't directly visualize. There's no point in space that's the center of expansion. Feynman loved using analogies like this, but he always warned, don't take the analogy too far. The balloon is just a model. The real universe is more complex, but the analogy captures the essence, uniform expansion without a privileged center. Now, if you reverse this expansion in time, if you imagine the universe shrinking instead of expanding, you inevitably arrive at a point where everything was compressed into an infinitesimally small space. This is the Big Bang. It wasn't an explosion in already existing space. It was the moment when space itself and time itself began to exist. Before that, the words before and after don't even make sense because time didn't exist. Feynman, being rigorous as always, pointed out that when we talk about the Big Bang, we need to be careful. We don't know exactly what happened at instant zero. Our equations break down. General relativity predicts a singularity, a point of infinite density and curvature. But that probably means general relativity isn't the complete theory. We need a quantum theory of gravity to understand those first instants. But we don't need to understand instant zero to understand why the sky is dark. The fact that the universe had a beginning about 13.8 billion years ago is sufficient. We can only see light from objects whose light has had time to reach us. And the universe's expansion ensures that light from the most distant regions is shifted to invisible wavelengths. Let's add one more layer of depth. The universe's expansion not only explains why the sky is dark, it also explains one of the most important discoveries of modern cosmology: the cosmic microwave background radiation. In the first moments after the Big Bang, the universe was incredibly hot and dense, so hot that atoms couldn't exist. Protons and electrons were separated, forming a plasma, and in this plasma, light couldn't travel freely. It was constantly absorbed and re-emitted by charged particles. The universe was opaque. But as the universe expanded, it cooled. And about 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine to form neutral atoms of hydrogen and helium. This event is called recombination. And when this happened, light could finally travel freely. The universe became transparent. The light that was emitted at that moment, the light from recombination, is still traveling through the universe today. But remember redshift. This light was emitted when the universe was about 1,000 times smaller than it is today. So it's been stretched by a factor of 1,000. It was originally visible light, orange and red light, corresponding to a temperature of about 3,000 degrees Kelvin. But after being stretched 1,000 times, it became microwave radiation, corresponding to a temperature of about 2.7 degrees Kelvin. And this is exactly what we observe. In 1965, two physicists named Arno Penzias and Robert Wilson accidentally detected this radiation using a radio antenna at Bell Laboratories in New Jersey. They were trying to eliminate noise from their measurements and noticed there was a persistent signal coming from all directions of the sky, uniformly. They couldn't get rid of it. At first they thought it was carrier pigeons nesting in the antenna. They cleaned the antenna. The signal remained. Eventually they realized they were detecting the afterglow of the Big Bang. They won the Nobel Prize for it. And this discovery spectacularly confirmed the Big Bang theory. The universe really did have a hot, dense beginning, and the night sky isn't completely dark. It glows faintly in microwaves, the echo of the cosmos's birth, invisible to our eyes but detectable with sensitive instruments. Feynman would be fascinated by this. Here's real light, light that's been traveling through the universe for more than 13 billion years, reaching us from all directions. If you had eyes sensitive to microwaves, the sky would be bright. But because your eyes only see visible light, the sky appears dark. Darkness is, in part, a limitation of our senses. The universe is screaming with radiation, but we only hear a small piece of the spectrum. And this cosmic background radiation has another incredible property. It's incredibly uniform. It comes from all directions with almost exactly the same intensity, differing only by 1 part in 100,000. This uniformity tells us that the early universe was extremely homogeneous. But these tiny variations, these minuscule fluctuations in temperature, are crucial. They represent small density differences in the early universe. And these density differences, amplified by gravity over billions of years, eventually became galaxies, stars, planets, and us. So when you measure the cosmic background radiation with precision, as was done by the COBE, WMAP, and Planck satellites, you're literally seeing the seeds of cosmic structure. You're seeing microscopic quantum fluctuations inflated to cosmic scales in the first moments of the universe. You're seeing the blueprint for everything that exists. Feynman would have loved the elegance of this. A simple problem, why is the sky dark, takes you through almost all of modern cosmology. Finite age of the universe, expansion, Big Bang, cosmic background radiation, structure formation, all connected, all part of a consistent and testable narrative. And each piece of the puzzle is confirmed by multiple independent lines of evidence. But let's add even more depth. The universe's expansion isn't just something that happened in the past. It's happening now, and it's accelerating. In 1998, two groups of astronomers studying type Ia supernovae in distant galaxies made a shocking discovery. They expected to find that the universe's expansion was decelerating, being slowed by the gravity of all the matter. But what they found was the opposite. The universe is expanding faster and faster. This discovery was so surprising that it took years to be accepted. But independent evidence confirmed it. And the leaders of the two groups, Saul Perlmutter, Brian Schmidt, and Adam Riess, won the Nobel Prize in Physics in 2011. But what could cause an accelerating expansion? Gravity is attractive, it should be slowing the expansion. So there must be some form of energy that exerts negative pressure, that pushes space outward. And this energy has to dominate the universe's energy content. Physicists call this dark energy. And honestly, we don't know what it is. The simplest explanation is that it's the energy of empty space itself, something Einstein called the cosmological constant. But we don't understand why it has the value it has, or what its fundamental nature is. It's one of the biggest mysteries in physics today. And this dark energy changes everything about the universe's future. If the expansion keeps accelerating, galaxies outside our local group will eventually recede so fast that we'll lose contact with them forever. The observable universe will shrink. Billions of years from now, astronomers in our galaxy will look out and see almost nothing. Just our local group of gravitationally bound galaxies in an otherwise empty, dark cosmos. They'll have no way of knowing that the universe was once filled with billions of galaxies, that there was a Big Bang, that the universe had a rich history. All the evidence will have receded beyond their horizon. It's a sobering thought. We live in a special time, cosmologically speaking. We can still see the cosmic background radiation. We can still observe distant galaxies and map the large-scale structure of the universe. We can still piece together the story of cosmic evolution. Future civilizations might not have that opportunity. The universe will have hidden its own history. Feynman would appreciate the irony. The same expansion that explains why the sky is dark will eventually make the universe appear even darker, emptier, more mysterious. And he would emphasize the importance of doing science now, of asking questions now, of figuring things out while we still can. Because the universe doesn't owe us answers. It doesn't wait for us to be ready. It just is, evolving according to physical laws that don't care about our curiosity or our understanding. We're lucky to live in a time when we can see far enough and measure precisely enough to reconstruct the universe's history. We're lucky to have telescopes that can detect photons that have been traveling for billions of years. We're lucky to have the mathematics and the physics to make sense of what we observe. But luck isn't enough. It takes work. It takes rigor. It takes the willingness to question everything, to not accept comfortable answers, to follow the evidence wherever it leads, even if it's strange, even if it's uncomfortable, even if it contradicts our intuition. That's the Feynman way. That's how real science is done. And that's what the darkness of the night sky teaches us. The universe is not infinite in age. Space is not static. Nothing is as it seems. Even the most obvious, most familiar phenomenon, darkness at night, hides layers of profound truth about the nature of reality. And those truths are accessible to us if we ask the right questions, if we do the calculations, if we make the observations, if we refuse to be satisfied with half answers and hand-waving explanations. The darkness reveals light, if you know how to look for it. If you enjoyed this and want to support the channel, give it a like and subscribe. It helps more than you know, and lets me keep making content like this, diving deep into the ideas that really matter. Now let's talk about something else the darkness reveals. When we look at the cosmic microwave background, when we measure its temperature and its uniformity, we're not just confirming the Big Bang. We're testing fundamental physics in ways that are impossible in any laboratory. The cosmic background radiation is the most perfect blackbody spectrum ever measured. A blackbody is an idealized object that absorbs all radiation that hits it and emits radiation with a specific spectrum that depends only on its temperature. And the cosmic background radiation fits this blackbody curve with astonishing precision. The COBE satellite measured it and found that it matched the theoretical curve so perfectly that when they plotted the data points, you couldn't see them because they were hidden beneath the theoretical line. That level of agreement between theory and observation is rare in science. And it tells us something profound. It tells us that the early universe was in thermal equilibrium. It had time to thermalize, to reach a uniform temperature before it became transparent. And that puts constraints on what could have happened in the very early universe. If you just had a simple Big Bang, where the universe suddenly appeared and started expanding, different regions wouldn't have had time to come to the same temperature. They would have been causally disconnected, meaning light wouldn't have had time to travel between them. So how did they all end up at the same temperature? This is called the horizon problem. And the solution, proposed by physicist Alan Guth in 1980, is cosmic inflation. The idea is that in the very first fraction of a second after the Big Bang, the universe underwent a period of extremely rapid exponential expansion. Space expanded so fast that regions that were initially close together and in thermal equilibrium were suddenly far apart. This expansion was driven by a special kind of energy field called the inflaton field. And when inflation ended, that energy was converted into matter and radiation, reheating the universe and starting the normal expansion phase that continues today. Inflation solves the horizon problem because regions that now appear disconnected were actually connected before inflation. They had time to thermalize, then inflation stretched them apart. Inflation also explains why the universe is so flat, why its geometry is so close to Euclidean. And it explains the origin of the density fluctuations we see in the cosmic background radiation. Those fluctuations are quantum fluctuations in the inflaton field, stretched to cosmic scales by inflation, and then amplified by gravity to form galaxies and stars. Feynman died in 1988, shortly after the inflationary theory was gaining widespread acceptance. He was skeptical of ideas that couldn't be tested directly. But I think he would have appreciated how inflation makes testable predictions. It predicts specific patterns in the cosmic microwave background. It predicts the statistical properties of the density fluctuations, and observations have confirmed many of these predictions. The Planck satellite, launched in 2009, measured the cosmic background radiation with unprecedented precision and found that the data fit the inflationary model beautifully. Not perfectly, there are still puzzles and anomalies, but the basic picture holds up, and that's how science progresses. You start with an observation. The sky is dark. You ask why. You develop theories. You make predictions. You test those predictions. Sometimes the theory fails, and you need a new one. Sometimes it succeeds, and you gain confidence. And slowly, piece by piece, you build up a coherent picture of how the universe works. The darkness isn't just an absence of light. It's information. It tells you about the universe's age. It tells you about expansion. It tells you about the Big Bang. It tells you about inflation. It tells you about the laws of physics operating on the largest scales. And it tells you something philosophical, too. It tells you that the universe has limits. There are things you can never see, not because they don't exist, but because the structure of space-time prevents their light from reaching you. There are questions you can never answer, not because you're not smart enough, but because the information has been destroyed or hidden beyond the horizon. The universe doesn't give you complete knowledge. It gives you a finite window, a limited view. And within that view, you have to do the best you can. You have to extract as much information as possible, make the most precise measurements, develop the most accurate theories. Because that's all you get. And yet, look at how far we've come. A few centuries ago, people thought the universe consisted of the Earth, the Sun, the Moon, the planets, and a sphere of fixed stars. The idea that stars were distant suns, that galaxies were vast collections of stars, that the universe had a history and an evolution, all of this would have seemed like fantasy. But through careful observation, through mathematical reasoning, through the scientific method, we've figured it out. We've measured the distance to stars, we've measured the distances to galaxies, we've measured the age of the universe to within 1% accuracy. We've mapped the cosmic microwave background. We've detected gravitational waves from colliding black holes. We've imaged black holes directly. We've discovered thousands of planets around other stars. We've determined that the universe is 70% dark energy, 25% dark matter, and only 5% ordinary matter. All of this from looking at the sky, from analyzing light, from asking questions and refusing to accept easy answers. Feynman would be proud. He always said that the joy of science is finding out how things really work, not how you wish they worked, or how they seem to work. And the reality is always stranger, always more interesting than anything you could imagine. The darkness of the sky is stranger than anyone imagined. It's not just the absence of light. It's a consequence of the finite age of the universe, the expansion of space, the Big Bang, inflation, and the fundamental laws of physics. It's a window into the deepest questions about existence. Where did we come from? Where are we going? What is the ultimate fate of the cosmos? And those questions have answers, or at least partial answers, that we've been able to discover by looking up and wondering why. So the next time you look at the night sky and see that darkness, don't just see emptiness. See the evidence of cosmic evolution. See the light that has traveled billions of years to reach your eyes. See the echo of the Big Bang glowing faintly in microwaves. See the distant galaxies receding into the darkness, carried away by the expansion of space. See the limits of knowledge imposed by the structure of space-time itself. See the beauty and the strangeness of a universe that doesn't care what you think, that operates according to laws you can understand if you work hard enough, that reveals its secrets slowly and reluctantly, but does reveal them to those who ask the right questions. That's the brutal truth Feynman wanted us to understand. The universe is dark, not because it's empty, but because it's young and expanding. We live in a brief moment of cosmic history when we can still see far and learn much. The darkness is information. The darkness is a gift. The darkness tells us where we are, when we are, and what the rules are. All we have to do is look carefully, think clearly, and refuse to accept comfortable lies in place of uncomfortable truths. The sky is dark. Now you know why. And knowing why changes everything. It changes how you see the stars, how you think about time and space, how you understand your place in the cosmos. You're not just looking at points of light scattered randomly. You're looking at a structured, evolving universe with a beginning and a fate, operating according to principles you can grasp. That's power. That's knowledge. That's what Feynman devoted his life to pursuing. And that's what he wanted to share with everyone who would listen. The universe is knowable. It's comprehensible. It rewards careful thought and honest questioning. And the darkness of the night sky, that simple, everyday phenomenon, is one of the most profound teachers we have.